Okay, today we're going to talk about risk condition vulnerabilities. So this is the outline of today's lecture. So what is a risk condition and the risk condition vulnerability and how to exploit the risk conditions and the countermeasures. So risk condition happens when multiple processes or threads access it and manipulate the same data concurrently. And the outcome of execution depend on a particular order. So normally, if you have multiple processes or threads to access the same data, you are going to use locks, such as a mutex. Then, after you finish with the data, you can release the lock. Without those locks, if you have multiple processes or multiple threads to access the same data, so it really depends on which thread getting the data first. So sometimes you will even get a wrong result. If your program has a risk condition, so the attacker may affect the program output by influencing the related events. So there are many ways to affect a program execution. For example, if we have a server, so the server will accept network input, right? So and also it could have a lot of timers and say the other processes. So look at those, the boundary between your target program and the external environment. For example, a server can accept network inputs, so the attacker can deliberately decide when a network packet is being sent to the server, or the timers. Okay, and also other processes. So when you have a machine which runs multiple servers, okay, so the execution of other process can affect the execution of your target program. So because they share the same hardware and they are through the time shared scheduling. Okay, so the attacker can use all those influences to control or to affect the program execution. So here we have an example that would be the Linux kernel dirty code exploits. So this is not the cow that makes milk, but instead this will be the short name for copy on write. So we're going to talk about this in more details later. So here is an example of withdraw function. Okay, so we want to withdraw some money from the bank account. We first get the balance. If the amount we want to withdraw is less than or equal to the balance, we subtract the amount from the balance. Okay, then we save the balance. So here there are three or four actions, right? So first, we get the balance. Second, we check whether the amount is less than the balance. The third, we subtract the amount from the balance. The number 4, we save the balance. Okay, so all those 4 different things, they can happen simultaneously if are running by 2 processes or 2 threads. If they are 2 simultaneous withdraw request. Okay, because there is no synchronization, bad things could happen. For example, if we have, say, $100 in the balance, now we have two threads. Okay, so they both get the balance of $100. Then one thread say, I want to subtract $50. So the other thread say, I want to withdraw $60. So because they both get the same balance of $100, this will proceed. So the first thread say, okay, we have $50 left. The second say we have $40 left. So depending on which process will be executed last, right? So the eventual balance will either be $40 or $50. So which should, which is a wrong result, right? So the balance will be negative $10. The real balance. So it shouldn't be even allowed to withdraw the money if we have a proper synchronization. So there is a special type of risk conditions, like time of check to time of use vulnerability. So it happens when checking for a condition before using a resource. Right? So this is a special type of risk conditions, which is common source of security vulnerabilities. So here is an example of time of check to time of use vulnerability. So here we have access. So the access check if the real user has the access right to a file. We know in the Linux or Unix system, right, file access is checked by permissions. So the permission is separated into three groups: the owner, the group, and the others. So for each group, we have three permissions: write, read, write, and execute. Okay, we have the read, write, execute for group, and the read, write, execute for others. So the access check if the real user has the access right. So normally the real user, real UID equals to a effective UID, right? Our UID normally equals to the effective UID. But in one situation, they can be different. That's the set UID program. In the set UID program, so the effective UID equals to the owner of the program. So the real UID will be the user of the program. Okay, so access will check the real UID whether it has the access rights to access a file, right? But the open here will check the effective UID, right? So the first line, let me erase this. So in the first line here, so it check whether the real UID can access this file. So the file is /temp/x. Okay, so if you pay attention here, so we see there is a negative operator here. This is because access will return 0, means it's OK to access the file. Any other numbers will be not OK. Okay. So if we say not 0, it means for this condition to pass, we must have not 0 to be true, right? So it means that the access to be the return value of access to be 0. So this means the real user can access this file. Then after the permission checked, so this is the time of check. After the permission check, we can open this file with write permission. So this is the time of use. Okay, so because there is no synchronization or the lock between those two operations, so those two operations, they are not atomic. So the atomic means that it's a whole piece. So that if you want to execute one operation, you must execute the other. But because there is no lock here, so those two operations are not atomic, right? So the attacker can execute something in between those two operations. So between the time of check to time of use. So this is why this kind of vulnerability is named as a time of check to time of use vulnerability. Okay. So in our example, right? So in the set UID program, we have the effective UID EUID to be root, and the real UID to be seed. So if the attacker can somehow change this temp file between the time of check and the time of use, so the attacker essentially can open the file with the effective UID, which is the root. It means that it can open any file, including the password file. So our target is to write to protect the files like etc password. So in the etc password, it's a password database. It contains the essential password information. Okay, so but we cannot change the file name or anything in the program because the etc password is owned by the root. Only root can read or write into this file. So this is not a executable, right? So this is the database. So this is the file contains all the password information. So when you type password, this will be the program. So this will be a set UID program on your system. So these are the two different things. So the etc password will be a file contains the password information. The password program will be the one you use to change your password. Okay. So the symbolic link can help us to achieve this. So what's the difference between symbolic link and hard link? Okay, so the symbolic link is actually a path. So the hard link will link to the inode of the file. Okay, so here you have a file, right? So this is the file. So the file has a number of information stored in the file system. So the hard link is basically another block of information linked to the file. But the symbolic link, it's actually path information in the inside the file itself. So okay, so the symbolic link just points to the file with the directory information. So the hard link is linked to the data of the file. So they are different. So here is how to attack this previous example. So we can create a regular file inside the temp directory. So the temp directory is a very interesting directory. It's accessible to everyone on the system. It means that it can be read and write by everyone on the system. But what if you create a temporary file and somebody else deleted it? Right, so we're going to talk about this later, okay? So we create a regular file x inside the temp directory. Then we change temp x to a symbolic link points to etc password. Okay, so here when we check the access, because the temp x file belongs to the seed, right? So it belongs to the owner is seed. Okay, so the access check will pass because the file is owned by the real user. Then when we can change the temp x to be a symbolic link over etc password. But now open will check for the effective UID, which is a root. Okay, then we can open the password file for write. So notice the timing is very important here. So for example, if you would change it temp x to the symbolic link before the access, okay, so the access will fail, right? Because it's symbolic link into the protected file, which is owned by the root. But the access will check against the real UID of seed. So if you have a symbolic link, right? So the operating system kernel notice this is a symbolic link. It's going to follow the symbolic link and found this will be the etc password file. Then the access will check the real UID against this file because this file is owned by root. So the access will return error, right? So the timing is very important. You must change the temp x to the symbolic link in between the time of check and the time of use. If we go back to the vulnerable program here, it means that in this step, so it must be the temp x file owned by C. Okay, so before the open and after access, we need to link the temp x to etc password. Okay, so the modern of computers, they are extremely fast, right? So the time window of this explorer will be extremely short. Right, so right after the access, we pass the check of access. Okay, we need to change this file to a symbolic link, and before the open. So the solution is the brute force attack. If you still remember in project 2, buffer overflows, right? So we can use brute force attack to overcome the address space layout randomization, right? So it will be actually very efficient because the SLR on 32-bit architecture only has about 2 to the power of 16 cases for us to brute force. But here, brute force is challenger because the time window is very small. So here we give a graphic representation of the attack. Right? So the temp X first points to attack owned file, then the access will check against the real UID, which will be the attack. So here in our example will be C. Right? Then a context switch will happen to the attack program, which will delete the tempx file and points it to etc password. So the context switch must happen in between the time of check to time of use window. All right. So now it can write to the etc password. Okay. So if you are not familiar with the context switch, right? So let's think about it in a simple case. If we have a CPU, right, a single core CPU, so you can execute one process, right? Because we cannot change anything inside the process. So you can execute one process. Then there will be a timer. The scheduling timer fired up when you're executing in this process A. So now with the timer, it enters into the kernel. So the kernel will reschedule the process. Okay, so it may pick a different process, say process B for execution. So for the context switch to happen, there must be a scheduling timer to fire in between the time of check to time of use window. But to make it even harder, because modern CPUs, they have multiple CPU cores. Like, for example, like 4 CPU cores are very common. Normally you have 8, right? So if you have a Ryzen, AMD Ryzen, sometimes you can have 24 CPU cores. Okay. So if you think about it, right? So if you only have a single attack program, which may be scheduled onto a different CPU core, will not affect the execution of your target program. So it will. So the time of check and the time of window essentially will be extremely small. Okay, here is another example. We have a file called tempx. So you can check whether the file exists or not. If file exists, okay, if the file exists equals to false, we can open the file with create. Then we can write to the file. So here is another example of time of check to time of use vulnerability. So the problem here is that in between the vulnerable window, so the attacker can actually create this file. Okay, so let's use the same kind of figure here. So the check file exists or not, then so the here is the file doesn't exist. Okay, so at this is TOC, this is the TOU. In between here, maybe there is a context switch, right? So the attacker can create this file. Now the vulnerable program will open the file with O create. So when you open a file with O create, it will only create if not exist. It means that if the file is already exists, so it will just open the file for access, for read or write. Now think about this, right? So when the vulnerable program checks the file exists or not, the file doesn't exist. Now the attacker will create a file at this place. Okay, so the vulnerable program then will open this file for access. So because this is a setUID program, when they open the file, it can access the file, right? Because the effective open checks the effective UID. So the effective UID is root here. So the vulnerable program will open the attacks file for write operation. So it's going to write, for example, sensitive information into a file owned by the attacker. So the attacker can access this sensitive information. So here is our experiment set up. So we have a file, a temp XYZ, get some user input, right? So then we check whether it's okay to access, then open the file. So here A plus means append, but without delete, without delete existing data, right? A plus means append to this file, but don't delete the existing data. We can, so it basically add something to the end of the file, right? So then it's going to do the fwrite, write the user input into this file. Okay. Then it's going to close the file. So it first write a return, then write the untrusted input in the buffer here. If we take a look at this program here, so this will be the untrusted input, right? So the buffer is untrusted. Then we open this file and we write the buffer into the file. We can build this program with GCC. Then we make it a setUID program, right? So we change the owner to root. Okay, so we're going to talk about this sticky symbolic link protection later. But for now, let's just disable this sticky symbolic link. So how do we explore the race condition? There are a few steps. First is to choose a target file. In our case, there will be the etc password file. Then we can launch the attack. So because this is a brute force attack, so we have two processes. One is the attack process. The other will be the vulnerable process. So they run at the same time, right? So the attack process will constantly to create a file, delete the file, and change it to symbolic link. Right? So the vulnerable process will be run multiple times in a tight loop. So try to access the vulnerable program. Then we can monitor the results and run the exploit. So here is our target. So we will target the etc password file by adding a new user. So here is a line in the we want to add to the etc password file. So this line contains a number of fields. Like the first field will be the username, then the hash value for empty password. So the password is just empty here for the test user. Then we set the UID to be 0. So here is the group ID. This will be the home directory. So here will be the default shell. Right? For each line in the password file, it actually contains those number of fields. So all your password in your Linux system is actually saved as a hash value. So the hash value or security hash function is a one-way function. It's a one-way function. It means that you can apply the function, right? So the y equals to a hash x, right? So this is the way to apply this function, but you cannot say there is no easy way to get x from y. Okay, so this function is very difficult or even impossible to find with limited computing resource. So this is why it's called a one-way function. You can calculate the hash over some value, but it's very difficult to find a value which will hash to a specific number. And this is so. There's other attributes of a hash function used in the security context. So, but normally your password are stored as the hash value. It's not in the plain text. So if you think about it, right? So if the etc password file is leaked and all your passwords are saved in the plain text, you basically gave all your user account to the attackers. But if they only get the hash value, right, from a password file, it's very difficult for them to find a password which will hash to be to this value. Okay, so this is why all your password will be saved as a hash in the password database. Now we can run the vulnerable program. We have two processes: the attack process and the vulnerable process. We can run the vulnerable process in an infinite loop. Here is such a loop, right? So it's a bash shell. So we have a while loop, and we execute the vulnerable program and redirect the password input. So the password input will be the content here. Okay, so this will be the content in the password input file in this page. So if we succeed, right, so we can append this user into the password database. So here is the attack program. So in the attack program, we first do the unlink temp XYZ. We then can symbolic link XYZ to this file. Then we sleep for a very short time. Then we can do the unlink, okay? Then we can do the symbolic link to etc password. Then we sleep for another short time. So we're doing this in an infinite loop. Then we can return 0, right? So it's not going to return here. So if we look at this, right, at the beginning, temp XYZ points to a file owned by the attacker, the seed here, my file. Then before the time of use, it's being linked to the etc password file. Okay. So we can also monitor results. So this will be in a shell script. We can monitor result here. So we can check the file. Okay, so the check file is a command here. So we get the old dollars, then this check file. Then we get a new dollar check file. So while old equals to new, we run the vulnerable program. We then update the new. Okay, so what's happening here, right? So the key to understand this script is to understand this structure. Okay, so the dollar check file is actually will be represented by this, replaced by this string. So the old actually equals to dollar, then parentheses, then ls-l-etc password. Okay, so this means execute this command, right? So this structure dollar with parentheses, it means that executed the command in between those two parentheses, right? So we're actually executing this command. Then the output of this command will be given to old. So the new variable will do the same. We'll execute this command again, and the output of ls-l will be assigned to new. Now we have two strings. If they are not equal, it means that so the output of LSL are the same, right? Then let's run the vulnerable program again. If they are different, right? If they are different, it means that the file has been changed. The etc password file has been changed, right? So now we can stop the vulnerable program because the password file has been changed. So we can take a quick look at the ls-l. We can take a quick look here. So if you look at the output of this command, right? So this will be the same. So this will also be the same. This will be different if the attack succeeded. This is the file size. So the file size will be different. So another thing that will be different will be this data and the time. So the data and the time will be updated to your current time. So the time when the etc password file has been overwritten. Okay, so if you will change anything in the etc password, we are going to have a different output from the ls command. Right, so the old and new will be different if the attack succeeded, right? So this is how this script works. So here we start a race. We run the attack process first. So this sign means running in the background. Then we run the target process. So the target process will be this batch, right? So this batch here, it will keep running the vulnerable program at the same time, check whether the attack succeeded or not. Okay, so it will stop the race, and we can check the password file over here. So it has been added to the password file. Now we can su test, and we give the password. So the password will be empty password here. So now we can get the root shell, right? So this is how the race condition exploit works in this example. So we're not going to demonstrate this because it may take a very long time to actually win the race. Okay, so next we're going to talk about the countermeasures. So the first countermeasure is to use something called atomic operations. So in the operating system, basically it means that we're going to use lock and unlock to protect those two operations. Right? So this will eliminate the window between check and use. So the second will be the principle of least privilege. Right? So if we think about this, right? So in the vulnerable program, when we do the access, we check the real UID. When you open the file, we're actually using EUID. And if we succeed in access, it means that the real user can actually access this file. So we don't need to have the effective UID to access this file. So the real UID can actually access this file, right? So we can, before the open, we can set the effective UID to be the real UID, right? So we can also repeat the check and use to make it more difficult to win the race. It's not a real fix, right? So we can check the, maybe check the access multiple times, right? It will reduce the window of vulnerability even further. There is also a sticky symbolic link protection. So again, this is a workaround. It's not a real fix. So the real fix will be atomic operation and reduce the permission or privilege. So in the atomic operation, if you try to access the file, use the FO exclusive. Okay? So it will create a file, and O exclusive means that it will return error if the file already existed. Okay, it will guarantee the atomicity of the check and use. If it's a temp file, we need to use a random name like make temp. In the general, we can use logs to avoid the risk conditions. So let's go back to the vulnerable program. If we look at this program, right? If we look at this program here, so if we add, say, mutex log here, and if we do mutex unlock here, so this piece of code is actually atomic, right? But this will not prevent this attack. So if we are using logs, so it will only become atomic if every process access this resource, use the same log. So if we have two processes, or let's say if we have two threads, both take the log and do the unlock. So here it take the log, okay? Then you will get the log here and do the unlock later. So only in this case, so the atomic or the logs will work, right? Because every process or every thread that use the critical section or that use the resource, they share the same log. So the log can provide the atomicity here. But in our example, right? So if we take the log, here, right? If we add the mutex log in the source code, so we have this vulnerable program which lock the text log and do the unlock here. Then we have a attack program, but the attack program doesn't care about the log inside the vulnerable program, right? So it can actually access the files. It can change the file, it can rewrite the file, it can unlink the file, it can link the file to a different file, right? So the attacker here, because it doesn't care about the log, right? So it can still launch the attack. So the logs like a mutex log, right? It will not provide a protection based on the file. So instead, we need to use the log, the file system log. Like the example here. Right? So we can use O exclusive to prevent any change to the file when we access the file, right? So in general, use logs to avoid the risk conditions. Again, so the logs will not help in this case. So here is another possible defense to repeat the check and use. So if you look at the program on the on the left side, we first do the access, right? Then we open it. So then we check the permission again, then we open it again. So now we have two file descriptors. Then we can do it again. We can get another file descriptor. So now we have three file descriptors points to the same file, the temp XYZ file. Then we can call the F state. Okay, we can call the F state to get the information about the file. If they are all the same file, so the state inode will be the first inode. Inode it contains the metadata about the file. So if they are the same, right, it means you actually write to the same file. Okay, so we actually try to check and open the files 3 times. Then we check whether those 3 FDs are the same, right? If you think about it, right, so this can significantly reduce the we can significantly reduce the possibility of time of check and time of use vulnerability. It means that the attacker not only needs to win one race, but it needs to win all those different races. But the code is ugly, confusing, and hard to maintain. So this is not a suggested way to prevent this kind of attack. So another way. So we have mentioned that, right? So another way is to do the principle of least privilege. So you basically between the time of check and the time of use, you're going to call the set UID program to set the EUID to real UID. Now, when we try to, so assume the attacker win a race, right? So the first access, it will point to the attack points the file, but in the open, now it points to etc password file. But because the EUID now is saved, right, the same as the real UID, so the attack will be prevented. So the last protection is the sticky symbolic protection. So we can permit the symbolic only to be followed with those 3 conditions. When outside a sticky word writable directory, okay, or when the UID of the symbolic and the follower match, or when the directory owner matches the symbolic link's owner. So this kind of protection is very ad hoc. So they try to address a specific problem. Okay, so it's not a very effective defense against other cases. So we're going to talk about this in a little bit more detail in the next slide. But what is the sticky bit? So the sticky bit is a permission bit that sets on a file or directory that let only the owner of the file or directory or the root user to delete or rename the file. So the sticky bit is normally used in the temporary directory. So let's take a look at the temporary directory. Okay, let's do the ls slash temper. Okay, so let's go to. So if we look at this, right, the temp directory, so the difference here, this is a T, right? So it's owned by the root and the root group. But the T means this is a sticky directory. So the temper is a sticky directory because every user have a right of access to this directory. If you look at this, right, so the R and the W, it means others. Every other user can read on the right into the temp directory. Okay, so what if, say, one user create a temporary file, but the other user try to write into this file or delete this file, right? It will be a disaster. So the sticky bits basically says that if you have a file in under the stick directory, right? So only the root user or the owner of the file or directory can delete or rename the file. Okay, so if you look at the temp here, okay, so this is on my own computer, so everything is owned by myself. But if we have a multi-user system, right, so it's going to have a temporary file from different users. So they all have the read, write, and the execute permission on those files. So the sticky bit basically solve this problem and says, okay, if it's not your own file, you should not touch it. Okay, so this is a workaround. It's not a fix of the root cause. So here is how to enable this permission or enable this protection. So here we have a simple program to experiment with the sticky symbolic link protection. So here is the result. So the symbolic protection will allow fopen when the owner of the symbol link matches either the follower or the EUID of the process or the directory owner. Okay, matches either the follower or the directory owner. So the follower will be who follows the link, right? So if we say, so if we have a symbolic link to say etc password. So when we follow this link, so when we do the permission check, we will follow this link. Okay. So the follower is actually equal to the effective UID of the vulnerable program. Then we have directory owner and the owner of the symbolic link. In our case, right, so the symbolic link is owned by the seed because it's created by seed, right? So our current user or the attacker. Then the directory, so the directory is /temper. It's owned by a root. So the follower is the effective UID of root. So because when we execute open, so it's going to check against the effective UID. Right? So the effective UID of our vulnerable program is root. So if you look at this, right? So the symbolic in the owner is the seed, and neither the follower or the director owner equals to seed. So this request will be denied. Okay? Oh, here, yeah. So we have a slide for the principle of least privilege. So if we look at the our vulnerable program, we first check the permission with access. So the access check permission with real UID. Then we open the file for access. Only if the access check passes. So if the access check passes, it means that the file can be accessed by the real user ID. So we don't actually need the effective UID in open to access the file. Okay, so we can set the effective UID to be the real UID before the open. Now, so the open still checks the effective UID, but the effective UID now equals to real UID equals to C. So when we follow the symbolic link to etc password, because this file is owned by the root, so the open check will fail, right? So this will prevent this attack. So here is how to do this, right? So we can get the UID. So this will be the real UID. Then we can get the effective UID. Then we can set the effective UID to be the real UID. Now we can open this file for write. Okay. After this, we can set the effective UID to be the old effective UID to restore the root privilege. So the principle of least privilege basically means that a program should only have the minimum privilege for its function. So it should not use more privilege than necessary for its task. So this is extremely important in set UID programs. So try to lower the privilege whenever possible. Okay, so this ends the lecture 4.